In her video about removing measurements, removing a collapse postulate from basically quantum mechanics, Mithuna had a very instructive video, and where she, said basically sort of the way of making measurements without making measurements, etc. Also in the Susskind lectures on entanglement, he describes the double slit experiment, and and he sort of covers similar ideas in a slightly different way. I think this here is basically sort of a synopsis of that, the shortest, least entangled or jumbled up way, I think, to summarize those ideas. So here it goes. Basically, the story usually takes place like this. You have here you have sort of like a tensor product state. So you have a state of let's say a particle and a measuring apparatus. So that the first entry is the first term here is the particle, and the second one is sort of like the measuring apparatus. And then you find out that if your particle is in state U, and the measuring apparatus is in this state ready to measure, then after some time it ends up, the particle ends up in state R, and the apparatus ends up in state P. And if the particle begins in this other state, again with the apparatus in the same way as before, then you end up with in this state where the particle ends up in state S and the apparatus in state Q. Now without apparatus, if you just let this, by the way, is unitary evolution, just as here, that arrow, that's what it means. So say you had the particle in state U. This is the state vector of the particle, and you let it naturally evolve, and it evolves into R. Same thing, V, you let it naturally evolve, and it evolves into S. Okay. If you look at this situation, where you later on plan to make a measurement, so you're going to make a projective measurement, but let's do something. Let's begin with a state that's a combination of this U and V, the simplest combination, the one with sort of equal probability. So you begin with U plus V, and you know that by linearity is going to evolve, the unitary evolution is going to be into R plus S. So now let's say that you want to do a projective measurement after that. So you want to take some kind of projection of this final state into some subspace E, and you're going to want to find sort of the probability of that. So you do this right here. Now when you expand this, right, this becomes P of R, P of S, P of R, S again. And after you do all that, you're going to get 4 terms here. Okay, and the PR, comma PR, and the PS, comma PS terms are going to be the usual terms or whatever, and then the mixed ones, P of R, comma P of S, are going to be the interference terms. So you can have 4 terms here. Okay. Now here, in this other situation, sort of describing the same thing, you have that you have the initial state U plus V of the particle, again half, probability of being in state U and half in state V, and you have the apparatus right here ready to measure, which happens by an interaction. So then you're going to end up, again by linearity and unitary evolution, into this. Now you want to do the same thing. You want to make take a projective measurement. So you do this, right? PE. This is just, the projector on the first particle, tensor with the identity on the measurement apparatus, a Hilbert space. So the first one is on the particle Hilbert space, the other one is on the apparatus Hilbert space. So you take this projective measurement right here. So you're going to do P of this thing, comma P of the same thing. All right. But this just breaks down into PE of the first terms here of R and S. sort of looking like before, and then the second terms are just going to be P and Q. Right? And when you do this, you're going to find out, since by the way the inner product on tensor product space breaks into the inner product on the first Hilbert space times the inner product in the second Hilbert space, you're again going to find 4 terms here, but the 4 terms are going to be like P of R, inner product P of R, times P inner product P, plus P of R, P of S, the inner product times a P inner product Q, and so on and so forth. So again, you're going to end up with 4 terms over here, just like here. But here you just had those 4 terms and that's it. Here, the fact that you're going to have it multiplied by P inner product Q and so forth, oftentimes, and for example in Mithuna's example and in Suskind's example, oftentimes this P inner product Q is going to be 0. So then the 2 interference terms, the ones that have the P and the Q, not the ones with P inner product P, but the ones, or Q inner product Q, but the ones that have P inner product Q, those are oftentimes you're going to be able to eliminate them, and that basically is what the disappearance of interference is. So it's sort of acts like a measurement without there being any collapse. Okay, so just wanted to show you this simple little derivation with minimal notation.